So I'm going to use this lesson to teach you about some of the cooler implications of number theory. So some of the interesting things we can do now that we have a little number theory background, just to show you the power of these numbers and why we care about all of this. So this talk is largely going to be about primes. And the motivation for this is that primes are a common topic among computer scientists and mathematicians. Like you'll hear in so many conferences, like people are always focused on like learning different things about prime numbers and why they're so important. And it's because they have a lot of useful mathematical properties. And probably the most popular application is going to be in cryptography. And so that's what we're going to talk about in this lesson is how we can use these prime numbers in cryptography, how they make it just so much more powerful. And before we get to that, I want to do some definitions and then some more discussion about primes. So first, let's just go over the definition of prime versus composite. So a positive integer is composite if it can be written as the product of two smaller positive integers. And so you can say n is composite if and only if there's two numbers a and b, two numbers a and b between 1 and n, such that n is a times b, right? So that you have like some, you can divide some numbers out of it other than just 1 and itself. And if a number is not composite, then it's prime. So then its only factors would be 1 in itself. Another really common theorem, I mean, you can tell it's important because it has fundamental in the title, is the fundamental theorem of arithmetic. And so the fundamental theorem of arithmetic basically just says every number can be written as a unique product of prime numbers. So every number can be factored out into primes, and it's always going to be like its own set of primes. So you're not going to have two numbers equaling the same product of primes. So an example is 100 can be factored out into the prime numbers 2 times 2 times 5 times 5. Similarly, 2020 could be factored out as 2 times 2 times 5 times 101. Now, this is an activity I want you to try at home because I think it really gives some good motivation as to why prime numbers are so important. Basically, if I give you a number n, try to use it to find the prime numbers. So like I just gave you like 2020 equals 2 times 2 times 5 times 101, right? But how would you actually go through that? And you can kind of think about like naively how we could do it. So like if I'm starting with 2020, I'll just start with like the first prime number I know, which is 2. See if that divides it. It does. So then I divide it by 2. And then I get 10, 10. And then again, I'll try with 2. Okay, that works. And then that's 505. And then, so then I'll try like the next prime number I know, right? Which is 3. So does 3 divide it? No, that doesn't work. Okay, I'll try 5. 5 does divide it. And then I get 101. And so like you can kind of just step through like the primes, and kind of get each of these like numbers. And then like I know 101's prime. So I'm good. Now I have my like prime factorization. I have all my, I know it's going to be 2 times 2 times 5 times 101. And so this is kind of like a naive strategy is what they'd maybe call it, because it's, we're just kind of stepping through. But this is actually like we haven't come up, the community has not come up with that much better of a solution. So when you're looking at a number, like that is usually the best solution, is still kind of going through, like there's some ways to speed it up, but you're still really just looking through and just testing the different prime numbers. And so like with 2021, if we were to take that approach, like, okay, we'll try 2, that doesn't work, we would try 3, you'd find out that that doesn't work. We try 5, that doesn't work. Try 7, that doesn't work. And then, you try 9, that doesn't work. And the reality is, or sorry, 9's not even prime. We try 11. But the reality is too, is that you really wouldn't just be trying the primes. You'd be trying like all numbers, because if not, you'd have to like have a way of saying that like this like of generating the next prime number. So like I have 2. Okay, what's the next prime number after 2? It's 3. What's the next prime number after 3? It's 5. And that's actually like not a given algorithm. Like, yeah, it seems easy here, but like once I get to like really high prime numbers, like, okay, once I get to 4, like this isn't even a high number, but once I get to 47, what's the next prime number after that? And there's not actually like an algorithm that can tell you like this is the next prime number after that, or at least not one that can efficiently tell you in a reasonable amount of time. So so you really have to be trying like every number. So if I'm trying 2021, I'd really be saying, okay, I'm gonna try 2, then 3, then 4, then 5, then 6, then 7, then 8, and none of these work. And so I'm just gonna like spoil it and tell you the first divisor is 43. And so like you can see how that would take a while to check every number until you get to 43. And this isn't like a very large prime number, comparatively. But like you can see already how it would be kind of tedious. And this is really like the fundamentals of cryptography, is that it's just really like hard in terms of time complexity to factor out these large primes. And I know that might seem silly here, but like let's try scaling it up a lot. And like we'll go to like this number. I am not going to read this number out. But this number is 617 digits long, and it's 2048 bits. It's also the product of 2 large prime numbers. So this number only has 2 factors, and they're large. And so this is the power of primes, right? Because if a number is prime, it doesn't have any factors. So I can have this number being the product of 2 large primes. That means that it's going to be it only has 2 factors, and those factors are going to be really big. And the reality is that a classical computer, it would take it around 300 trillion years to factor out this number, to find out what those 2 primes are that make it up. And so this is the foundation of RSA cryptography, and why we care so much about primes is that if the harder a number is to factor, we can really leverage that. So now let's talk about like cryptography and like kind of the theory behind it. So say I have Alice and Bob. And so Alice wants to send a message to Bob. And she wants to be able to Alice wants to receive a message from Bob. So Bob has this briefcase that he wants to share with Alice. And so Alice is going to say, okay, I have my padlock, and I'm going to send my padlock over to Bob, but I'm going to hold on to the key. I'm just going to go ahead and unlock it. So that way he can just like put the padlock on the briefcase and send it back to me. But like he doesn't have the key to my padlock. So in case I wanted to reuse this padlock, that's fine, because he doesn't have the key. He wasn't able to like copy it or anything. I have the key. I just send it to him unlocked. And then now I can, unlock the briefcase and read whatever secret message it was, or whatever secret contents that Bob was trying to send. Now, say that there's also Chris, and Chris has a briefcase. Well, Alice can send that same padlock unlocked to Chris. And Chris can again, lock the briefcase with that padlock and send it back. And let's say Bob's feeling like a little nosy and wants to kind of see what's in that briefcase. Like, I wonder what Chris is sending Alice. Well, Bob doesn't have access to the key because Alice has kept that key by herself the whole time. She sent the padlock to him unlocked. So he doesn't like know how to unlock a locked version of this padlock, in other words. So the idea is that like you can use this padlock multiple times with different people, and like using the padlock with someone doesn't teach them how to use it. And you can, she can use it now for like multiple messages between other people. So when Chris sends her the briefcase, Bob's not able to kind of eavesdrop in and, unlock that padlock and get that information. So this is actually really the idea of cryptography. So this unlocked padlock, this thing that you're sending to other people that they can use to like privatize what they're sending you, is called your public key. And the idea of like them kind of, using that padlock to lock in the information in the briefcase, that's called encryption. And the private key, so that key that only Alice had, is used to decrypt the messages. So decrypting the message can be thought of as just unlocking the padlock and actually seeing the contents inside of the briefcase. So this is the idea of encryption and decryption. And like, it demonstrates the importance of, just because someone's able to encrypt something doesn't mean they should be able to decrypt something. So those are kind of like the important rules. The act of locking and unlocking, aka encrypting and decrypting our lock, shouldn't alter the contents of our message, right? So when I'm messing with my padlock, I shouldn't be, destroying anything in the briefcase. And as I said before, observing the public key shouldn't give you any information about the private key. So having access to that padlock, that doesn't mean like you're able to unlock the padlock, right? Having access to an open padlock shouldn't give you any information about how to unlock it when it is locked. So this can be done numerically. There's a type of encryption that you can do basically with mathematical operations that lets you encrypt and decrypt messages. So the kind of information you'd be encrypting and decrypting would really be like strings of words, right? So here we're really like thinking about just sending like, like hello or something like that. Like that would be maybe like the secret message I want to encrypt or decrypt. For the sake of our purposes, we're going to be doing something more simple, like encrypting the number 2 or 3, like just encrypting a number. But like the idea is you want to be encrypting like some type of message that I could be sending to someone, over the internet. But because it's encrypted, only people who have access to the private key should be able to actually like decrypt it and read it. So the public key is something, again, that anyone has access to, and it's a number n. So it's going to be denoted by this big N, and it's going to be a multiple of 2 numbers, P and Q. And your private key is going to be dependent on P and Q. So they need to be difficult to figure out, right? Because you don't want anyone knowing your private key. So it needs to be difficult to figure out what P and Q is. So even if you know N, you shouldn't be able to figure out P and Q. And so, now we know how to do that. We can just make them really large prime numbers. And if N is the product of 2 really large prime numbers, P and Q, we know we can't, like, even if we have N, we don't know how to factor out N. So we don't know how to get P and Q. And so this is kind of like the foundation of like how you choose your public and private key, is that you choose this big number N that's a product of these 2 smaller primes, and then these 2 large primes, and these are used to kind of create your private key. And since it's dependent on that P and Q, like it's really hard to figure out. And so no one has like the computing power to figure out P and Q. So now I'm going to talk more like about like actually the step-by-step process of like, okay, I have a message and I want to like encode it or encrypt it and then decode it or decrypt it. And say we're just sending the number X. So this is what I said, where it's like, it's just going to be like the number 2 or something like that. And so your public key is going to be this number E, and this letter N. And so I already kind of showed you how we're going to get N, and it's going to be that product of P and Q. And I'll talk more about what E is, but E is really like, E stands for encryption. So your public key is going to contain these 2 pieces of information, and your private key is going to include it is going to include N, and that's okay, because D is really the thing you don't want people to figure out. And of course, D stands for decryption. And so the way you encrypt a message, say your message is X, so that's a number. So like we said, like the number 2 or the number 3, you basically take it and raise it to the power of E and then mod it by big N. And that'll give you your encrypted message Y. Now, with my private key, I can apply, I have Y now. I take Y and I put it to the power of D, and I mod it again by big N, and it should give me back the original X. So this X right here that I encrypted, it should give it back to me by taking it to the power of D mod N. And so again, like we have our 2, important rules, the act of locking and unlocking, aka encrypting and decrypting our lock, shouldn't alter the contents of the message. So if that's just basically saying if I take it to the power of E and I mod it by N, and then I take it to the power of D and mod it by N, I should get the same message back, right? And so this property needs to be true. And then observing the public key can't give you information about the private key. So given E and N, you shouldn't be able to figure out D, right? And so those are the 2 properties that we're really like counting on to make this encryption work. So the first part of RSA is, now say we already have our N, which is a P and Q, like, it's a product of P and Q, our 2 big prime numbers. And so we have N. Well, we need to pick an E and a D. So we need to pick like what number we're going to use to encrypt and number we're going to use to decrypt. And we can't just choose any number, because as we already said, like they have to have those properties of like, to the power of E, then to the power of D has to like give you back X. And also like, even if you have E, you shouldn't be able to figure out D. So we need those kind of properties to be true. So there's kind of a trick to how you pick E and D. And so one fact we're going to use is if a number is congruent to 1 mod P minus 1 times Q minus 1, then so we have R here that's equivalent or congruent to 1 mod P minus 1 times Q minus 1. Then if we take any number to that power and we mod it by N, then we get that number back. So you can already kind of like maybe see what this is implying, right? Because if we make R E times D, then X to the E times D mod N would give me X. So like that would give me, exactly what we were talking about, where like if I take it to the power of E and to the power of D, then I'm going to get the original message back. So we kind of want to use that property. So basically we want it to be true that E times D is equivalent to 1 mod P minus 1 times Q minus 1. So that is basically how we choose our E and our D. And then that gives us our property. So, okay, cool. Our property is met, that now we can encrypt and decrypt, and we get back our original message. That was our first kind of requirement. Now, remember, our second requirement was, though, like, even if I do know E and N, I still shouldn't be able to figure out D, right? Because D is private. I should only know that because I need to be the one who knows like what to decrypt. And so what I did was that let's just kind of reason about like what the attacker knows in this situation. So say we had Bob trying to eavesdrop in. He knows E and N because that's part of your private key. So everyone knows your private key, E and N. He also does know like that this is true, that X to the E, and if you take it to the power of D and mod it by N, you'll get X back. And he's even done that because he sent a message. So he knows this. He still doesn't really know necessarily what D is though. And he knows that, like, because say he just knows the rules of encryption, he knows that you chose an E and a D such that E times D is 1 mod P minus 1 times Q minus 1. And he also knows that N is going to be the product of two primes, P and Q, but he doesn't know what P and Q are. So these are, I'm just kind of just high level talking about what the attacker knows. And let's kind of think about each of these. So for this property here, x to the e time to the d mod n equals x, he knows that it's true. But the thing is like, again, he knows e and he knows n, but like d could be many things. And that's because you're using like this mod operator. D can be a lot of different things. So 29 to the 3 mod 33 could be 2, but also 29 to the 13 mod 33 could be 2. 29 to the 23 mod 33 could be 2. So like e times d could be many different values, right? Because like this exponent here is our e times d. And like, so like, this e times d could be many values. And so you don't know like what d necessarily is. So this like fact that we kind of have like use this mod operator makes it hard to figure out what this d is. And that kind of helps us with that property. It kind of shows, okay, so they can't get that information. Like even if they know this equation and they know e, they still can't really figure out d, because e times d could be many different things and still give you like the same output. Now, they also know that e times d is equivalent to 1 mod p minus 1 times q minus 1, right? Because we kind of say they just know RSA and they know that property, but they don't know p or q. So they're not really able to like use that information because they don't know how to do like this side of the equation. And finally, they know that n is the product of p and q, but again, they don't know how to find p and q given n, because it would just take so much time, computationally to find p and q. So this is like the main theory behind RSA cryptography. Is really this idea that like these prime numbers are so powerful. Like all of this rests on the fact that p and q are just so hard to factor out. So given e and n, you can't figure out d. And so this just shows you the power of prime numbers, and also like how RSA cryptography works, and the theory behind it, and how like I know math can be kind of daunting and frustrating, but it has some really cool implications.